Hey, P Statistics. So welcome to section 8.3. In 8.1, we got the idea of confidence intervals. 8.2, we focus on confidence intervals for proportions, population proportions. Here, we're going to focus on means. We're dealing in quantitative data. There's an actual population mean mu. We're going to use an X bar to produce a confidence interval. By the end of this section, you should be able to determine the critical value for calculating a C% confidence interval for the population mean using a table or technology. You should be able to state and check the random, 10%, and normal large sample conditions for constructing a confidence interval for a population mean. You should be able to construct and interpret a confidence interval for a population mean and determine the sample size required to obtain a C% confidence interval for the population mean with a specified margin of error. So a lot of this stuff is going to sound a lot like, very predictable, but there's kind of one really key weird thing that shows up this section. So here's what the formula you might think. Oh, sorry. Here's our confidence interval for a population proportion. So we used our statistic plus or minus our z star, our critical value, times our standard error of our statistic. That was our estimate for that standard deviation using p hats instead of p. But that's the general idea of our statistic plus or minus critical value times the standard deviation of a statistic. All right, so if we try to do that for a confidence interval for X bar, it would look like this. We would go X bar plus or minus, and then you might think Z star, and then sigma over root n. So that would be a one sample Z interval for a population mean. And it's kind of straightforward. That's what you would go with. You would find your X bar from your sample. You would find Z star in much the same way you did up here. You'd find sigma. You'd actually have to be given sigma. And then you divide by the square sample size. You got yourself a confidence interval. You're on your way. The problem is that's not actually how it's going to go down. In reality, if we don't know the true value of the mean, it's not likely we're going to know the standard deviation, which measures the typical distance from the mean. So we aren't actually going to know the population parameter sigma. So we can use S instead, just like we used p hat up here, right? Well, kind of. Up there, it's not a very big difference, swatching p hat for p. Over here, there is kind of a consistent difference. So what we notice is, let's say we use S instead of sigma, but things don't work quite like they should. So if we use S, and what they've done here is they calculated a whole bunch of intervals, and I'll show you kind of how this works, but notice those intervals, our widths are changing because we're using different S's. Each sample has a different width, and even though in this case we're looking for a confidence level of, let's see, this was 95%, or our success rate is only 92.5, so we're not quite getting that success rate that we were looking for in this case. So out of those that they've done so far, we're not hitting it quite enough. So they're doing a actually I'm mistaken. This one was a 99% confidence level, but they're only having a 92.5% success rate. So because of that, we have to make an accommodation for that rate. We're just not, if we use S instead of Z, that rate is off. With proportions, it's actually, it may be slightly more or less, but it's not unbiased. It's not going to be biased in a particular way. Here, we're less likely to be successful in capturing that parameter. So we need to account for that, account for the additional error of using S instead of sigma. So to achieve a 99% capture rate, we need to multiply by a larger critical value. But what should we use? So this creates the problem, makes the problem a little bit more complex. We're going to have to use T instead. This T distribution, somebody came up with this to give us a slightly wider range, and it accounts for that additional error of using S in place of sigma. So the critical values of T star has generally the same interpretation as the mean. It measures how many standard deviations we need to extend from the point estimate to get the desired level of confidence, and it's just slightly wider. So if you look here, the normal distribution is this purple curve going up through here. The T distribution's a little bit wider, so it gets a little bit shorter in the middle, a little bit taller on the tail. So and then what we use is we use degrees of freedom And so depending on how big your sample size, it affects how much extra additional error it is. And so we end up being a little bit more spread out than our normal distribution. And so as that sample size, at a smaller sample size, it's actually more spread out. You see this dotted line. So in degrees of freedom, in this case, it'll depend on what we're doing, but in this case, it's always n-1, the sample size of -1. So 2 degrees of freedom would be for a sample size 3. It's a little flatter, and it's got this curve's a little more spread out. And so you gotta go further to cover the same percentage of the distribution, whereas, you know, as we go up to 9 degrees of freedom, it gets closer and closer to the normal curve. And as that sample size increases, eventually there's not this additional error from using S instead of sigma. It kind of goes away. So if you have a large enough sample size, you can pretty much do a Z interval, but we'll generally be doing T intervals for for this situation. So here's how this actually is going to go down. We choose our confidence level, and so we're going to do our confidence interval this way. We're going to choose our point estimate X bar. We're going to go plus or minus T star, where that's our critical value from the T distribution. It's this slightly wider distribution, and so I'm going to show you how to get the values from that. There's a table, but basically it's just a new command. Instead of using normal CDF, you use TCDF. Instead of using inverse norm, you use inverse T. So you can do that. Where we use n-1 degrees of freedom, the sample size -1 is the degrees of freedom. That relates to that n-1 in the denominator. We see that come up in a few different places. That is what we'll use for T star, and then we use S in place of sigma. And so this is actually the formula that we'll use to create our one sample, what we call T interval for a population mean. A one sample Z interval for a population mean does exist if for some weird reason we know sigma, and in that case we can use Z. If not, if we're using S in place, we need to use a T distribution, a T critical value. So what critical value T star from table B should be used in constructing a confidence interval for the population mean in each of the following settings? So confirm your answers using technology. So you've got a table in the back of your book here, and I can give you a printout of this as well, but again, I don't recommend it. And so this is the T distribution. It's table B. And so what you do is you actually choose, the T distribution depends on your sample size. So degrees of freedom in this case is n-1. So you choose a particular row to use. And it's actually kind of nice. Actually, the T distribution, I knock the tables, but this one's actually a little bit better. It's kind of easier to look up because it's better for critical values. You look up specific tail probabilities if you want to find probabilities, and you can even look down at the bottom and you've got confidence levels. And so it's actually pretty easy to find some of those. And if you, even in the bottom row, you have this infinity, that's actually the normal distribution. So you'll recognize some of those numbers, like 95% is 1.96, 90% is 1.645. You know, you might recognize some of those, 2.576. So not terrible altogether, but that's one way that you can find, use your table to do this. So switching back, in this case, what we're trying to do is a 95% confidence interval for based on a simple random sample of size 12. And so our degrees of freedom that we're going to use is 11. And so we're going to look in the 11 row, and then you could look at 95% confidence for that bottom row. And so if you kind of go up from that bottom row, you can look there. Notice that tail probability is that 2.5%. We've kind of done that logic before, where each tail would be 2.5% because that middle 95%. And so that critical value we're going to use is a T star of 2.201. That's how many standard deviations, really standard errors, we need to go from the mean. What if we want to do a 90% confidence interval with a sample of 48? Well, you'll notice that there's a little bit of a problem here. If you look in that table, you'll see that there isn't actually 47 would be our degrees of freedom, but there is no 47. It starts skipping by tens, and then eventually it kind of goes nuts and does a few high numbers. As the sample size gets bigger, it basically becomes, you know, approximately normal. So what you can do is just go with the conservative degrees of freedom. That's what's recommended, though I've seen the AP test accept the rounded, and so you could go up to this one. But you go with that conservative, and so you can get a T star of 1.684 by choosing the 90% confidence level, that particular column, and then the conservative 40 degrees of freedom, 1.684. Turns out that's not actually the best answer. turns out you can be more accurate than using the table. And you can do both of these with inverse t. So if you do inverse t and then you type in the tail area 0.025 and then the degrees of freedom, it'll give you a t star, and it'll just be quick and easy. It's a lot like normal CDF. Inverse t, tail area 0.05, t star, actually you can type in 47, or sorry, degrees of freedom, and it will give you the t star of 1.684. All right, so that's finding our critical value. So then to actually check, to do this whole process, you need to check the conditions as well. And so this is the same as last chapter. The random condition is critical for doing inference. If the data don't come from a random sample, you can't draw conclusions about a larger population because there may be bias. But likely is bias if it's not random. When sampling without replacement, the 10% condition ensures that our formula for the standard deviation is approximately correct. We can treat it as independent. And then the last condition, normality, can come from a couple of things. So this still exists, but we need to have a large sample to ensure that it's appropriate to use a t-distribution to calculate the t-critical value. The t-distribution is based on normal, so really we need to assume that our sampling distribution is approximately normal, even though we don't know what the standard deviation exactly is of that. And so this checks to make sure that a t-distribution is appropriate for use. But again, that's the kind of the normal condition. I would be fine if you just say that, we have a normal sampling distribution, either from the normal population or the large sample size. So reminder, checking those conditions, we got the random, the 10%, the n is less than 10% of the population size, and then the normal condition. We can either have the population be normal, the sample size is large, n greater than 30, or if the population has unknown shape and n is less than 30, you can use a graph of the sample data to assess normality of the population. So they actually are going to let us make an assumption that if our graph looks pretty close to symmetric, bell-shaped maybe, no strong skewness or outliers, we can still kind of make that assumption of approximate normality. And that, it's kind of a mix. Maybe the population is not perfectly normal, but we have some sample size. Maybe it's not quite 30, but a large enough sample size to kind of overcome the non-normality and be able to use t procedures. So, for example here, determine if the normal large sample condition is met in each of the following settings. To estimate the average GPA of students at your school, you randomly select 50 students. Here is the histogram of their GPAs. So, here's the histogram of that sample. We don't actually have to worry too much about this. Our sample size is large. 50 is big enough. So our sample size is large. CLT covers us. We're going to be, approximately normal for our sampling distribution, and so a t interval is going to be appropriate. Second example here, only 20 selected, looks skewed. Not good, right? There's too much skew, maybe even outliers in this thing. This is not good. So the stem plot is strongly skewed to the left with possible low outliers, and the sample size is small. So not good enough. And then in this one, suppose that you want to estimate the mean SAT math score at a large high school. Here are the box plot for the SAT math scores for a random sample of 20 students at the school. So yeah, so 20 is not big, but this doesn't look terrible. There's a little bit of a longer whisker here, but that's not bad. That's a slight enough skew so that I just want you to realize it's not going to be perfection, that this would actually be okay to do this procedure. So yes, even though the sample size is small and the box plot is only moderately skewed to the right and there are no outliers. So with the sample size of 20, we should be enough for central limit theorem to kick in and cover us for having approximately normal sampling distribution, so we can do t procedures. AP exam tip, if a question on the AP statistics exam asks you to construct and interpret a confidence interval, all the conditions should be met. However, you are still required to state the conditions and show evidence that they are met, including a graph of the sample size if the sample size is small and the data are provided. So you need to actually check all those conditions. They should be met, right? If they're going to give you the problem, they should be met, and if you have to make assumptions, you need to make them. And if they don't seem like they're quite met, just kind of go with it, maybe state some concern, but you should be able to do that whole process. And that's what we're going to take a look at in the next video.